Welcome back to another lecture on space robotics. Today we'll be talking about flight software. This lecture will cover a system-level view of flight software to support robotic operations so that we can fulfill mission objectives. Let's define what we mean by flight software. At a high level, flight software is the onboard system that governs a robot's behavior. From controlling actuators to managing data to deciding how to respond when things go wrong. It's not just a block of code. Flight software includes bootloaders, fault detection routines, autonomy engines, sensor interfaces, and data logging systems. You can think of it as the brain and nervous system of a robot in space. Without it, nothing would work. Commands wouldn't get executed, no data would be collected, and certainly nothing would recover from faults. In this diagram, I've labeled anything that represents either hardware or subsystems in white, and data or algorithms in yellow. These are the lifeblood of the flight software system, the information it handles and the logic it applies. At the center is the onboard computer, where the executive algorithm coordinates system-wide behavior. It sends operation commands to the payload, all the way over there, and in return receives science data. It communicates with the communication system, handling commands from operators and returning data to transmit. It uses a mode controller to interact with the power system, adjusting based on state of health data. It uses mobility algorithms to guide navigation systems, which return robot state information and accept target site instructions. Inside the system, clock and storage modules track time and memory, key resources for managing events and data products. This structure shows how flight software reaches across every subsystem to maintain coordination, safety, and productivity, even when it's far from home and out of communication. Now that we've defined what flight software is and how it spans everything from component drivers to mission-level autonomy, let's focus in on one of its most critical responsibilities, data handling. On a robotic mission like Curiosity, bandwidth is limited and communication windows are short. Flight software plays the gatekeeper role. It decides what gets downlinked and when, and what can wait to be dropped altogether. This diagram shows that responsibility in action. On the right, we have the rover's core software stack, the onboard computer, memory, timing, and the communications encoder. On the left, you see the rover's uplink and downlink path through a Mars orbiter back to Earth via the Deep Space Network. Each orbiter pass lasts about 8 minutes per sol. In that time, uplink from Curiosity to the orbiter can hit up to 2 megabits per second, which means maybe 15 megabytes up to 120 megabytes of science logs and telemetry can be sent if conditions are perfect. That's like 10 to 100 medium resolution phone images. But for downlink, the orbiter can only send commands and updates back to the rover at 32 to 128 kilobits per second, which is just about 1.9 to 7.6 megabytes or 1 to 5 medium resolution photo images. That's a tiny fraction, and it means that flight software has to prioritize exactly which instructions are needed to move the mission forward. This balancing act, deciding which images, which sensor logs, which faults reports makes the cut, all happen through a combination of onboard logic and ground tools. But the execution, that's all flight software. So when we say flight software is the brain and nervous system of a space robot, this is exactly what we mean. We just talked about the first key role of flight software, prioritizing what data to send through a tight and unpredictable communication pipeline. But the next challenge is just as important, compressing and packaging that data to make the most of that limited bandwidth. On this slide, we're zooming in on the connection between the payload, which captures raw science data, and the onboard computer, which decides how to handle it. That data has to be processed, compressed, and stored before it can ever be downlinked. The 3 cat images that you see over here show different levels of JPEG compression. On the left is the original full-quality image, sharp, beautiful, but large. In the middle is the medium compression, the kind of image a human might still want for science. And on the far right, that's an aggressively compressed version, blocky but small and fast to transmit. This is where the distinction between lossless and lossy compression comes in. Lossless means no information is removed. It's ideal for critical data like telemetry and engineering logs. Lossy sacrifices fidelity for file size, which can be okay for some science imagery depending on the mission's needs. Flight software, and sometimes even the payload software itself, makes this trade-off in real time. What needs to be preserved at full quality? What can be compressed or even discarded to save space? That decision can affect data quality, scientific return, and even whether errors get caught in real time. So it's not just about getting the data off the planet, it's about making it small enough to fit without losing what matters the most. Compression in packaging isn't just for science images. It's also crucial to how the robot knows where it is. This slide gives us a different flavor of compression. It shows how the GNC system, or Guidance Navigation Control System, especially sensors like LiDAR or stereo cameras, can generate massive terrain maps to analyze the surrounding environment. That top image is a raw terrain scan, high resolution, full of data points. The lower image is the same scan with elevation and structure highlighted. But here's the key, none of that gets downlinked in its raw form. Instead, flight software distills all of that into just a few numbers, 3 values for position and 3 for orientation. That's a full 6 degree of freedom state estimate, the minimum needed for a robot to understand its place in the world. This conversion from heavy sensor data to a lightweight, actionable robot state estimate is a form of semantic compression. We don't need to keep the entire map. We just need to know, where am I? And which way am I pointing? And just like with image compression, this process needs to be accurate, fast, and efficient, especially when those values drive safety-critical operations like driving, drilling, or landing. So once again, flight software plays the role of information distiller, taking the raw measurements of the environment and packaging it into something useful and small. Now let's talk about the third major responsibility for flight software, reacting to real-time events. Unlike prioritizing and compressing, which help manage limited communication with Earth, this role is all about acting in the moment, when delays make human input impossible. In deep space, flight software isn't just about running background tasks. It's the only decision maker on board. Take Perseverance's AutoNav, for example. Its navigation software uses onboard sensors and terrain models to plan and adjust its path without Earth intervention. If it encounters a hazard like a rock or trench while driving, the rover doesn't wait for instructions. It autonomously finds a safer route. That level of autonomy is only possible because the mobility algorithms on the rover can process environment data in real time and make decisions on the fly. We can also see this in the Aegis system over there, which is part of the Science payload software. Aegis lets Perseverance autonomously select and prioritize rocks for closer inspection when time is limited or communication is constrained. This is incredibly useful during idle or transitional periods when human teams can't quickly respond. Together, these examples highlight how modern flight software isn't just a passive system, it's an active, responsive, and deeply integrated into how space robots think and move. It's what gives a robot the ability to do meaningful science, even when no one's watching. Another critical responsibility I want to highlight is logging events and telemetry, the memory of the mission. Everything the robot does, its movements, its hardware status, its science activity outcomes, needs to be captured, time-stamped, and stored for 2 reasons: mission safety and scientific accountability. That's why on this slide, the storage box is front and center. It's where all the robot's experiences get logged, from the health of the electrical system, to the science data processed by the payload, to the state of the robot's mobility system. All of those logs then get transmitted to a mission control center where tools like the Science Activity Planner come in. What you're seeing here is a real visualization used by operators to replay what the rover did. These logs help mission teams verify that commands are executed correctly, understand what happened if something went wrong, and plan next steps based on the robot's actual state, not just intentions. This function, capturing and packaging telemetry, may sound passive, but it's absolutely essential. Without these logs, we lose the ability to debug, learn, and advance our exploration efforts. And from a flight software perspective, it means handling huge volumes of structured data with precise timing, clear context, and selective prioritization for what gets sent back when bandwidth is tight. In a sense, data handling isn't just about what happens on the robot, it's about making sure the team back home can continue to think and plan with the robot. Probably the most critical role in flight software is handling faults. Let's shift to the inevitable reality of robotic missions: faults. No matter how robust your plan, anomalies will happen. It's not a question of if, but when, and how you respond. In space, faults aren't rare, they're expected. Radiation flips bits, sensors disagree, motors get stuck, and when they do, there's no reset button, no technician, no quick phone call to Earth. The robot has to detect what's wrong and know what to do next. What you're seeing here is a network of fault types and the kinds of things that can typically go wrong, and the recovery strategies that flight software uses to respond. Let me walk you through a few examples. Let's say the flight software crashes, maybe due to a bad loop or a logic error. A watchdog timer kicks in, detects that the software has frozen, and triggers a reboot. This kind of automatic self-check is essential to survive in deep space. Or imagine a bit flip in memory caused by cosmic radiation. That might be caught by the onboard error correction code, which silently fixes it. No reboot is needed. It's logged and the system keeps going. Now suppose that the power starts dropping. Maybe the solar panels are shaded or the battery is low. In that case, flight software initiates load shedding, a power-saving mode where it shuts down non-critical systems to keep the core alive. Other times, the problem is more physical. Let's say a sensor mismatch might signal a bad reading from an IMU or star tracker. Here, software might switch to a backup or reweight the data and continue operating in a degraded state. Then there are issues like instrument overheating or a jammed robotic arm right here. These often trigger what we call operator intervention. The robot logs the problem, halts the task, and waits for human input. And finally, if things are truly uncertain or cascading, like a corrupted command file over here, or multiple anomalies in a row, the rover or robot will drop into safe mode, where it points its antenna at Earth and waits. It's not ideal, but it's survivable. What's important here is that the flight software doesn't just run the mission, it protects it. It keeps the system stable, prevents problems from getting worse, and buys time for operators to respond. In every case, it's the first and fastest line of defense for your mission. Earlier in this lecture, we focused on the flow of information between the onboard computer and each subsystem. This slide shows more of a layered view of flight software, one that captures how the robot's intelligence is organized and encoded across different levels of abstraction. At the top, we have placed the onboard computer running what we call the executive algorithm. This represents the mission-level software, which manages overall behavior. It's responsible for high-level logic like fault management, navigation, planning, and data prioritization, answering the question of what is the robot trying to do right now. Beneath that is the subsystem level. We find the major functional blocks like communications, power, mobility, and payload. These systems are governed by autonomy modules like mode controllers, mobility algorithms, and data manipulation routines, each responsible for controlling an entire subsystem. This is also where you'll find control loops, watchdog systems, and logic that interprets health telemetry and translate high-level commands into executable actions. At the bottom, we enter the component level, where the software interfaces directly with hardware via drivers and low-level managers. This includes things like motor controllers, state of charge estimation, modulation, and image processing, things that run tightly coupled to real-time sensor data or actuator control. Again, the yellow highlight where software logic lives, whether that's high-level planning or a low-level real-time controller. The white boxes represent either hardware or core physical subsystems they govern. Together, this hierarchy illustrates what it means to encode a mission in software, from logic that decides what samples to take down to the motor control that deploys something like a drill. The previous slide talks about the different layers of abstraction by intention for flight software. This slide contains the same content but labels the layers of the software by the logical layers of application, manager, and driver. Each layer builds on one below it. Drivers talk directly to hardware, reading sensors, toggling actuators. Managers handle logic and control loops at the subsystem level, and applications coordinate behavior across subsystems to meet mission goals. Said in a different way, these application-level programs, these are mission-specific programs running on the onboard computer. Fault management is a system-wide watchdog. It checks if something has failed and kicks the system into safe mode. Navigation decides where to go next based on science goals or operator interaction. Data management decides what to store, what to downlink, and what to throw away based on bandwidth and importance. The manager level, these are software components that oversee an entire subsystem. The encoder in the communications subsystem formats and routes packets coming in and out of the spacecraft. The mode controller in the electrical power system decides when to turn components on or off based on system state. The state of charge estimator for the battery tracks how full or depleted the battery is based on voltage, current, and temperature. Mobility algorithms manage rover motion. They translate high-level goals like go to Site 3 into wheel commands. The visual odometry manager above the stereo camera processes images to estimate motion. In the payload, data manipulation includes things like image stitching or spectroscopy pre-processing before anything is downlinked. The image processing software over there may enhance or compress the data before it goes to the data management system. At the bottom is the driver level. These interface directly with the hardware. The communication protocol driver talks to the internal data bus, like SpaceWire or CAN. The modulation driver handles RF signal encoding for the radio, turning digital bits into radio waves. Charge regulators directly adjust power flow from the solar panels. Low-level control for motors over here sends pulse width modulation or torque commands. It doesn't decide where to go, just how to execute a move. And finally, the camera driver handles the interface to the image sensor. You can see there can be overlap in the logical layer of software as it belongs to the subsystem or component. So across these layers, the flight software stack enables raw voltages and bytes from hardware to become intelligent and autonomous, and vice versa. Understanding these layers helps you design software that's modular, testable, and ready for extreme space environments. So far, we've looked at kinds of software that are needed to run a space robot, from low-level drivers to high-level mission applications. But now let's talk about who builds all of that. This diagram breaks down the organizational structure of a typical flight software team. It highlights that, just like the software itself, the engineering roles are layer 2, from mission-level systems thinking to component-level development and testing. At the top, we have the Mission Software Systems Engineer, the MSSE. They're responsible for end-to-end architecture and making sure the software aligns with the overall mission objectives. They think at the application level: navigation, science objectives, autonomy behaviors, and how all the pieces come together. That's what I want you to do throughout this course. Supporting them are the engineers like the Data Systems Engineer, DSE, who ensures all telemetry and science data get collected and processed, and the Instrument Software Systems Engineer, ISSE, who focuses on payload-specific software needs. These engineers often live in the manager layer, especially for payloads and custom sensors. In the middle are technical leads, the people making sure actual code bases come together. The flight software lead engineer oversees the integration of the entire flight software stack, from application logic down to real-time loops. The autonomy technical lead focuses on decision-making systems, such as state machines, fault recovery, and onboard planning, which I would also like for you to put on the hat of. The testbed technical lead ensures that all of this software can be tested realistically on the ground with the right simulation environments, which we won't really cover in this course. Their team maps to all 3 layers: driver, manager, and application, but they specialize in the subsystem level: mobility, power, comms, and other. And finally, at the base of the organization are the developers, the subsystem team, and component specialists. They write drivers for motors and sensors. They build the test control loops for batteries and radios, and they work under subsystem leads who ensure their piece fits under the larger puzzle. Whether you're writing code to modulate a radio signal or designing a terrain-aware path planner, your role in this structure depends on which layer of the software you're touching. The takeaway here is software roles mirror software structure, and no matter where you're working, you're contributing to one unified mission. Now that we've talked about the different kinds of flight software and the engineers who implement them, let's take a step back and look at the bigger picture of development. Here is the full development lifecycle of a space software system. This diagram lays out the multiple phases of development, from planning all the way through delivery and long-term maintenance. It's a process that applies across the entire software stack: applications, managers, drivers, everything. But in this class, we're going to focus mainly in this area, in the early chunk, planning through architectural design. These phases are where the real foundation is laid. You start with your mission goals and requirements. What data do you need? What hardware are you working with? What level of autonomy is required? Then comes the architectural design, which is where your project's behavior, how it responds, how it flows, how it recovers, really takes shape. This is exactly where your concept of operations timelines and state flow diagrams come into play. Think of your software flow diagram you're building as an artifact that belongs to this phase. It's a tool that shows how your robot will function, how data moves through the system, and how software modules connect. This architecture isn't just theoretical, it's the scaffolding that informs what needs to be coded, what needs to be tested, and how to verify that the robot behaves as intended. Later in the lifecycle, during implementation and test, this early design becomes the reference for unit tests, integration tests, and even acceptance testing. So building a clear, thoughtful diagram now isn't just a learning exercise, it's a real reflection of how flight software gets built in practice. Let's zoom in on one of the most powerful tools in the software design toolkit, the state flow diagram. These diagrams matter because they force us to lay out logic explicitly. They help developers visualize what the system is doing at every step, identify edge cases before they happen, and enforce modular thinking. Instead of coding chaos, you get structure. And structure is what makes autonomy in space actually work. Let's break this example down. This diagram represents a basic concept of operations for a satellite. You can think of each block as a mode or a major task the system performs. These are your verbs in your concept of operations timeline. And just like in your assignment, each verb represents an operational state. The flow begins with the system in an initial mode where it boots up and initializes subsystems. If everything checks out, labeled here on the entry condition init OK, the satellite transitions to a safe mode. From there, you see the nominal working state, nominal mode, and a deorbit sequence later in the mission. Errors can kick the system into error mode. You can see that if the issue is resolved, the system transitions back into a safe state. So there's the error mode, and then back. This is what happens within those major blocks. To the right, you'll see some nested or expanded flows. This is what happens within those major blocks. For example, what's involved in initializing the satellite bus. Each of these could be its own flow diagram nested inside a higher level mode. What matters here is that each state has an entry condition. So the entry condition for safe mode is init OK, what triggers it, a set of actions, so what happens inside, and a clear exit condition, like error or set nominal work. For your assignment, you'll be doing exactly this. Every row in the ConOps spreadsheet becomes one of these blocks or decisions. You'll be building a visual map of how your robot transitions from task to task. And just like this satellite does, except tailored to your mission and data products. So whether your robot is navigating to a site, taking a sample, or waiting for a command uplink, think of that as a state. And remember, if you can diagram it clearly, you're halfway to implementing it successfully. As a reminder, in this lecture, we defined the critical role that flight software plays broke down flight software at a systems level in levels of abstraction and types of software, and walked through the process of flight software design in anticipation for you to design flight software that can support your space robotics mission objectives.